To install the Talos and joblib Python libraries using pip, you can use the following code.
"bash pip installed talos joblib ".
Talos is employed for optimizing hyperparameters in machine learning models, whereas joblib is utilized for creating lightweight pipelines in Python. This code snippet is used to set a specific seed value for random number generators in Python, NumPy, and TensorFlow.
By doing this, it helps to ensure that the results obtained are reproducible.
The code also includes the importation of different libraries like Seaborn, Pandas, Talos, Matplotlib, joblib, and Keras, which are commonly used in data analysis and machine learning projects. Moreover, it imports modules that are dedicated to data preprocessing and constructing machine learning models with TensorFlow. This code snippet changes the style of a plot generated by the Matplotlib library to the Seaborn style. Seaborn style enhances the appearance of the plots, making them more visually attractive and easier to interpret. This code opens a file named preprocessed_data_pg.npy that contains preprocessed training, validation, and testing datasets saved as numpy arrays. It uses numpy's load function to load these arrays from the file into variables x_train, y_train, x_valid, y_valid, x_test, and y_test. Then it prints out the shapes of these arrays to display their dimensions. The code reads preprocessed data from a file and then displays the shapes of the datasets that have been loaded.
These datasets are structured in a format where the dimensions represent batch size, time steps, features. The code snippet y_test is a variable name commonly used to store the actual output labels for test data in a machine learning model.
These labels are essential for comparing the model's predictions with the real outcomes to assess its accuracy. In essence, y_test contains the true values of the test data, crucial for evaluating the predictive capabilities of the machine learning model. This code uses the load function from the joblib library to load a pre-trained PowerTransformer model named PowerTransformer_close_PG. It then assigns this model to the variable called scalar. The code introduces a function called network_shape_customized, which receives inputs such as params, last_neuron, and network_type. This function works by determining the arrangement of neurons in hidden layers, according to different shapes and settings specified in the parameters.
When the layer's parameter is set to 0, the function will return a list containing only the number 0. It checks the type of shape given.
When the shape is a decimal number, it determines the number of neurons in each layer by considering the reduction percentage indicated by the float value. When the shape is designated as brick, each layer will have the same number of neurons as specified in the first _neuron value for the designated number of layers.
When using a funnel shape, neurons are arranged in a decreasing pattern from the first neuron to the last neuron.
When the shape is set to triangle, the neurons are organized in a triangular formation. This is achieved by creating a list of neurons that starts with a small number and gradually increases to a peak number before decreasing back down to the original number of neurons. When the system does not recognize the shape given, it generates an error. It provides a list that shows the number of neurons in each hidden layer based on the selected shape and parameters. The function hidden_layers_customized appears to be incomplete because it does not contain any code implementation. This code creates a function called LSTM_FN that trains an LSTM model using given training and validation datasets. It accepts inputs such as learning rate, ALR, and optimizer type, optimize, to compile the model. The LSTM model is structured with an input layer, variable hidden layers, determined by the provided parameters, a dropout layer for regularization, and a dense output layer. To train the model, the mean squared error loss function is utilized along with a specified optimizer using a designated learning rate. During the training process, early stopping is used to avoid overfitting. Once training is complete, the training history and the trained model are provided as output.
At the end, there is a parameter dictionary called para.
It includes various options, such as batch size, number of epochs, shapes, number of neurons in the first hidden layer, number of hidden layers, type of optimizer, and learning rate. These options can be adjusted and tested to enhance the training process of the LSTM model. This code uses the scan function from the Talos library to tune hyperparameters for an LSTM model.
It takes x_train and y_train data, hyperparameters, para the LSTM model function, LSTM_fn, and necessary tuning process parameters.
It specifies the experiment name as hyperparameter_tuning and includes x_valid and y_valid data for validation. Additionally, it enables a progress bar and displays the hyperparameters used during the tuning process.
This code uses the TPOT library to read and analyze data from a CSV file.
It creates a report object named R by specifying the file path.
The data in the report is sorted based on the val_loss column in ascending order.
The code then displays the top 10 rows with the lowest validation loss values. This code computes correlations between the variable val_loss and a set of other variables, loss, val_loss, round_epochs, LR, and hidden_layers, using the function rcorrelate. The resulting number ranges from -1 to 1, representing the strength and direction of the relationship between val_loss and each variable.
Values closer to 1 or -1 signify strong positive or negative correlations, while values closer to 0 imply weak or no correlations. This code creates a visual representation showing the relationships between the validation loss and different specified variables loss, val_loss, round_epochs, LR hidden_layers. By plotting a correlation matrix, it helps to understand the correlation among these variables and how they are linked to the validation loss. This code calculates the model ID by finding the index of the minimum val_loss value in the data array. It converts the val_loss values to float and subtracts 0 from the index to obtain the final model ID.
When you see the term model_ID in a code, it usually represents a unique identifier for a specific model or object within a system. This ID helps differentiate one model from another.
However, without more context or code examples, it's challenging to give a precise explanation.
Feel free to provide additional details or snippets for a more in-depth explanation. This code creates a function named plot_loss. It requires a dictionary with keys loss and val_loss as input. These keys contain training and validation loss values for each epoch. The function then generates a graph displaying these values, with epochs on the x-axis and loss values on the y-axis for both training and validation data.
This code extracts the final training loss value from the loss key of the model_history dictionary.
Typically, loss values in model training represent training loss values recorded during the training process. By extracting the last element from this list, we can obtain the final training loss value after the model has finished training.
This code retrieves and returns the latest validation loss value from a model's training history data stored in a dictionary under the val_loss key.
This code creates a function named save_best_model. It requires 3 parameters: scan_results, model_ID, and model_name. This function clears the session of the Keras backend. The code loads a previously saved model architecture using the function model underscore from underscore JSON, and it does so by retrieving the architecture from the scan underscore results using the specified model underscore ID. The model loads saved weights using the function set underscore weights from the scan underscore results. It generates a condensed overview of the model. The model is saved to a file with the name best underscore model underscore name. At the end, the model is returned.
Outside of a function, the save underscore best underscore model function is called with the arguments scan underscore results, model underscore ID, and model underscore name LSTM.
The resulting model is then assigned to the variable named model. The code creates a function called plot underscore model underscore summary, which generates a visual representation of a given model. The function takes two inputs, model and model underscore name. Inside the function, it uses another function called plot underscore model to create the visualization showing the shapes of each layer within the model. The resulting visualization is then saved as a PNG file named model underscore summary underscore plus the model underscore name. To visualize a model named LSTM, the defined function calls another function called plot underscore model underscore summary. This function needs the model as a parameter, which is assumed to be defined outside the code snippet. The visual summary of the LSTM model is then saved as a PNG file for analysis and visualization. This code creates a function called prediction that uses a given machine learning model to predict outcomes based on a test dataset named x_test.
The function then returns these predictions.
Once the function is defined, it is called with a specific model as an argument, model to generate predictions.
These predictions are stored in a variable named prediction_LSTM, which contains the model's output on the test dataset.
This code line reverses the transformation of scaled or normalized predictions from a machine learning model. It achieves this by using a scalar object to apply the inverse transformation. This enables the predictions to be returned to their original scalar format, making them easier to interpret and analyze. This code reverses the transformation done on target variables that were previously scaled using a scalar like min-max scalar or standard scalar. It ensures that the targets are returned to their original values, so they can be used in their natural form for modeling or evaluation, rather than the scaled format. This code creates a function named plot_future that generates a graph comparing predicted future stock prices with actual stock prices for a specified model.
The graph helps visualize how accurately the model predicts future stock prices.
The function has three parameters. A prediction is an estimation of future stock prices that is produced by a model. Model_name refers to the name of the model that was used to generate predictions.
Y_test represents the actual future stock prices that are utilized to assess the accuracy of the model's predictions.
The function is defined first, and then the code uses this function to generate a plot that compares actual future stock prices Y_test with predicted future prices made by a long short-term memory LSTM model. The plot shows the accuracy of the LSTM model's predictions in forecasting future stock prices. This code creates a function called evaluate_prediction that computes and shows performance metrics like R-squared, coefficient of determination, mean absolute error, root, mean square error, and max error, to assess the accuracy of model predictions. Depending on the step_ahead variable, the function has two different pathways. When step_ahead is equal to 1, the function computes performance metrics for a single step forecast. It utilizes functions such as mean_squared_error, mean_absolute_error, and R2_score from the scikit-learn library to determine these metrics and display them. If the step_ahead variable is not equal to 1, the function computes performance metrics for multi-step forecasting. It produces RMSE and R-squared scores in a table for each step within the forecast range. A visual representation of these scores is also generated. Furthermore, it calculates the overall performance metrics across all steps and displays them for reference.
Afterwards, the function is used for evaluating the model by providing it with predicted values prediction_LSTM, actual values y_test, and the model name LSTM.